Hello, this is Algebra Master, and this is episode 2 of Blindly Mathematical. In this episode, I will be talking about the three cubes problem. The sum of three cubes problem is a problem in which you take three numbers, called cubic numbers, which are formed by taking positive or negative whole numbers to the third power. So, for instance, these numbers would be numbers of the form 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, and so on. But you could also go with the negative versions of those, negative 1 cubed, negative 2 cubed, negative 3 cubed, negative 4 cubed, negative 5 cubed, negative 6 cubed, and so on. And just for the sake of simplicity in the problem, we're also going to include 0 to the third power because that's just 0, so technically that's also a cube number. And in the three cubes problem, we have to find three numbers, x, y, and z, such that x to the third power plus y to the third power plus z to the third power equals some other whole number. The goal of the three cubes problem is to find what whole numbers can be constructed in this fashion. So far, all numbers from 1 to 100, except for a set of exceptions, which I'll go over in a minute, have been found. So far, some of the exceptions that have been found are 4, 5, 13, 14, 31, and 32. So these numbers all have interesting properties. The properties being, of course, that they can all be written in the form 9k plus 4 or 9k plus 5, where k is some whole number. And in another video, I'll explain why these numbers can't be constructed. It has something to do with modular arithmetic, which I'll explain in another video. That will come in episode 5. So for now, those numbers I mentioned, 4, 5, 13, 14, and 31 and 32 can't be constructed because, well, 4 and 5 are 9 times 0 plus 4 and 9 times 0 plus 5, respectively. 13 and 14, 9 times 1 plus 4 and 9 times 1 plus 5. Then after that, you have 9 times 2 plus 4 and 9 plus 2, or 9 times 2 plus 5. So that means I forgot 22 and 23. So actually, so far, the complete list would be 4, 5, 13, 14, 22, 23, 31, and 32 all can't be constructed. But so far, all other numbers, if you exclude the ones that can be made using this 9k plus 4 and this 9k plus 5, all other numbers from 1 to 100 can be constructed and have been constructed, except there's one number that doesn't fit any of these rules, and it still lies between 1 and 100, and we have yet to prove it. That number is 33. So the problem x to the third power plus y to the third power plus z to the third power equals 33 has yet to be proven. Much in the same way as the Collatz conjecture, people have tried by brute force just plugging in numbers to the computer, seeing which numbers work and which ones don't. We have yet to find a solution, and also in the same way, they have checked numbers of humongous size, many powers of 10 high, and still to no avail, making many people question this problem: is it possible? This problem, it isn't so much the same as the last problem in the sense that we have to prove something for an infinite number of cases. If we look at just the case with 33, we just have to find at least a single solution. And then, at least for now, I mean, then other problems may come up, like how many solutions are there, because some numbers have infinitely many solutions. For instance, 1 you could write as 7 cubed plus negative 7 cubed plus 1 cubed. Well, 7 cubed plus negative 7 cubed is just 0. So if you take any cube plus its negative, you're going to get 0. And 1 is a cube number, so you could just take the two opposite cube numbers, add them together, and get 1. So that's how you could have an infinite number. So you could have 1 cubed plus negative 1 cubed plus 1 cubed. You could have 2 cubed plus negative 2 cubed plus 1 cubed. You could have 3 cubed plus negative 3 cubed plus 1 cubed, 4 cubed plus negative 4 cubed plus 1 cubed, and so on. If you keep continuing this pattern, you could definitely infer that there are an infinite number of solutions, because there are an infinite number of combinations of numbers you could try this with. And surprisingly, these aren't even all of the solutions. There's also other solutions you can try, but those solutions are much harder to find. Those are just the low-hanging fruit, so to speak. And those are the ones that, well, mathematicians like finding them and everything. They like to find the really hard ones to find because they're the ones that reveal the truly profound mathematical truths. Surprise, surprise. I mean, I can't really say I blame them. I mean, who wants to do what's easy? That's just boring. If you can do what's really difficult, find all the hard solutions, then it really creates a true feeling of mathematical satisfaction. So, is there a solution to this problem? Maybe, but so far, many mathematicians are convinced that there isn't, and their guess is as good as mine. The best tools we have so far to deal with this problem, well, the best tool that we know of, would be modular arithmetic. Modular arithmetic is all about dividing numbers into groups based on their divisibility. So, for instance, if your number is divisible by 2, we call that even, and if it's not, we call it odd. But why divide things by 2? You could also break things up into 3 groups. You could say, so there are the numbers divisible by 3. There are the numbers that are 1 more than a number that's divisible by 3. So, for instance, your number is divisible by 3. You got 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, and so on. But for your number is 1 more than a multiple of 3, so we would say that these numbers, mod 3, which means after division by 3, they'll have a remainder of 1. So if we say numbers mod 3 equal 1, this group, this set of numbers, then that would be numbers like 4, 7, let's see, 4, 7, 10, 13, 16, 19, 22, 25, 28, 31, and so on. And if you notice, each of these numbers are 1 more than the numbers from our previous collection of numbers. Then, we could also look at the numbers that are 2 more than a multiple of 3, such as 5, 8, 11, 14, 17, 20, 23, 26, 29, 32, and 35, and so on. So after, this follows a similar pattern. All of these are too bigger than some of the numbers than the numbers from our previous list. Well, from our original list of multiples of 3. Knowing this, we can pretty much break up all the real numbers, or all the whole numbers, I mean, into 3 sets. Those, mod 3, have a remainder of 0, so those that are divisible by 3. Those that when you divide them by 3 have 1 left over, and those when divided by 3 you would have 2 left over. I exclude those that are divisible by 3 would have 3 left over because those are just, well, divisible by 3. That extra 3 would just count as, and adding 1 to, your quotients, which is the result you get by dividing. So if you had 9, which is divisible by 3, and add 3, you get 12, which is also divisible by 3. This will always be true. If you take any multiple of 3 and add 3, you will always get another multiple of 3. So that's about all we know. We can get general truths, we can obtain certain general truths from these collections of numbers, much in the same way that you can obtain general truths about evens and odd numbers, such as what happens when you add two evens, add an even to an odd, multiply, subtract, divide them. You can do the same thing with these numbers mod 3. So if you take a number mod 3 equals 1, a number mod 3 that equals 2, and add them together, or a number mod 3 that equals 0, all these things will give you different properties and and they will give you numbers from these different sets. So that's all I have to tell you on the 3 cubes problem. This was episode 2 of Blindly Mathematical.